Here, Ava and I are going to prove the first two parts of Part C on the adventure sheet on cosets, that is, right cosets and congruence modulo k. So the first part here is to prove that A is congruent to B modulo k if and only if A is in KB. So first, Ava, remind me, what does it mean for A to be congruent modulo k?
So according to the definition we have in the sheet, it means that a b minus 1 is in k.
Okay, so we want to show AB minus 1 is in K if and only if A is in KB. So if AB inverse is in K, that means that AB is equal to K for some K, for some little k in big K.
B inverse.
Thank you. Okay, and what does that mean? Well, I know that because we're working in a group that I can multiply on the right here by B. So I get A, B inverse B equals KB. So this tells me that A is equal to KB, but KB is an element of the coset, big K, little b.
Okay, so I feel like you've done that direction.
Yep.
But everything can be reversed. So A is here, big K, maybe I should make my case bigger. And big KB, if and only if it can be written like this. And now all these steps that Becca wrote are equivalences. You can go from here to here easily. And yeah.
So that proves the other direction.
And we didn't have to do anything else.
Great.
The second is prove that congruence modulo k is an equivalence relation. So I'm gonna write.
What does it mean to be an equivalence relation?
It needs to be reflexive, symmetric, and transitive. So maybe we should write what that means in our setting. So reflexive means that any element is congruent to itself.
Okay. So we want to show A is congruent to A. Which means what?
That A inverse is in K for all A.
A inverse is in K for all A. But this is true because A inverse is always the identity, and K is a subgroup, so the identity is always in K.
Yeah.
Great.
Okay, symmetric means that if A is congruent to B, then B is congruent to A.
Want to show. So what does that mean? If A is congruent to B, that means AB inverse is in K. We need to show that this implies that BA inverse is in K.
But BA inverse is AB minus 1 inverse.
And again, K is a subgroup, so every element of K has an inverse. So I think what we just showed is that BA inverse is BA inverse is AB inverse, and we know AB inverse is in K.
So we're good. And transitive means that if A is congruent to B and B is congruent to C, then A must be congruent to C. So let me write that.
I'm going to erase so you have a little bit more space.
Thank you. Okay. So for transitive, we want to show that if A is congruent to B and B is congruent to C, then A is congruent to C. This is what we want to show.
Yes, and so we're assuming that AB inverse and BC inverse are in K, but we know that K is closed under our operation, which means if we take AB inverse times BC inverse, we get AB inverse BC by associativity, and this is the identity. So this means that
C inverse.
thank you, AC inverse, this was in K. AC inverse is in K.
So that's what we wanted to show. So
Exactly.
this is an equivalence relation. It satisfies the three properties.
Great. So part 3 is a discussion question, and we'll direct you towards Canvas for that. And then part 4 we will prove in the proof of Lagrange's theorem, part D, so that proof is self-contained.